All right, welcome. Thanks everybody for taking the time out of your day to come hear me talk a little bit. This is my 9th reInvent. It's been almost a decade now of this, and I really appreciate the fact that people are still interested in coming to hear what I have to say. My name is Rick Houlihan. I'm the field CTO for Enterprise at MongoDB. Some of you may know me from my days at AWS. I have a pretty long history in NoSQL. This is actually my second stint here at MongoDB. I was originally on the Enterprise SA team about a decade ago before coming to AWS. And originally I kind of felt like I thought I'd left the NoSQL technology arena at the time, but there was a little service called DynamoDB that called me up, and I was the first specialist solutions architect for DynamoDB. Spent many years on this working with the service team to help customers, and eventually found my way to Amazon Retail, where I spent a couple of years working on the project we call Rolling Stone, which was the deprecation of Oracle from our environment, and eventually became actual removal of the relational database platform from our Tier 1 application services. And I led the Black Belt team for NoSQL technologies, which defines some of the best practices and design patterns used by Amazon. And that's a little bit about what we're here to talk to today. It's really what does it mean to design, for the workload, right? What is good performance? And because that's really a lot of what my team does. It helps customers understand, how to use the technology most efficiently, so that they can make better decisions and have better experiences working with that technology. And what that comes down to is performance. So what does that mean? What does it mean when we talk about good performance? And then we're going to get into breaking down some of the myths, right? How does this really work? When we talk about putting the data together, modeling data relationally, or relational data efficiently in a NoSQL database, right? What's the process that we go through to make that happen? And what that really means is putting it in context, putting the data model in the context of the workload, right? Correct does not always look the same. What works well for one use case and one workload might be a disaster if I use that same data model in another. So, how do we kind of distill all of this information into a data model that actually fits, that workload? And what that comes down to is aligning the schema to how the data is used, right? Developers need to start thinking about how the data actually accesses the data, because this is what we're going to use. That information is what we use to actually build, effective schema. So the first thing we'll talk about is, what is good performance? And good performance really comes down to, a couple of dimensions and the various lenses we look at the application through in various ways. And one thing that we look through at the application is response time, right? Good performance is good response time. What does that really mean? Well, the expectation these days from the database is it's quick, right? It's milliseconds or less to get the data back out of the system. So, that can be one dimension that we look at in the system. And there's many, many dimensions, but these are really the four that I find that people talk to when I get into the design reviews and the discussions with customers. What is another one we might look at is throughput, right? How the application and the workload can handle, multiple transactions concurrently to increase the throughput of the system. Another dimension that we look at is efficiency, right? How well are we using the system resources, the CPU, the memory, the disk, and how efficiently are we actually using the system? And then the last dimension that I find to be what people are most concerned about is scalability, right? How does the system perform? Does it perform well when we increase the number of users, when we increase the workload, the size of the workload that we're working with? And the impactors in these areas really come down to some of the same things. And it all revolves around inefficient use, of the data, right? How is the system actually using the data, right? In response time, if we're having poor response time, oftentimes it's because we're doing more work, right, than we need to do. We're moving more data than we need to move. And we're going to get into this when we break down the schema. But we're doing a lot more work than we need to do to process the request, right? That's going to impact our response time. Throughput is similar, right? Complex queries, right? Things where we're making too many requests for small bits of data, right? This is a real bad impact in NoSQL data models. When we're storing data in too many containers and we're retrieving those data from separate containers, all the requests that we're making can start to impact, the throughput of the system. Efficiency comes down to not paying attention to how the system is actually accessing the data, right? We start to build large documents, embedded rich data structures, and we start to update little small pieces of data within these structures. It's not a really efficient way to work with the data. And so we're not paying attention to how the system's actually accessing the data. How is it using the data? If it's using the data in bits and pieces, then we should build a data model that represents how the application is using that. And then scalability comes down to poorly distributed workloads, right? I'm nailing too much work to a single shard. I'm creating hotspots in the cluster, whatnot. These are the things that we want to kind of start to look at when we start to talk about performance and what's impacting our performance. Now, if in relational databases, when we model things, we really do things in this third normal form, right? Third normal form is something we're all very familiar with as developers. We were taught this in school. It's how we use data. It's how we visualize data in our brains, right? Multiple tables, relationships between tables. In this case, we can look at maybe a content publishing or a forum type of schema, right? We have articles, we have people, we've got comments on those articles. All these things live in their different tables. They're homogeneous data structures, rows on tables. Articles might have tags, they might have comments. And when I want to query the data, I'm going to send a complex query down to the system, and I'm going to say, join these tables in this way to retrieve this result, right? Now, in the relational database, that's a lot of overhead that is incurred when I make that query, right? Joining the tables is a high time complexity operation. In MongoDB and NoSQL databases or document databases like MongoDB, we have choices about how we're going to represent those relationships, right? In the relational database, we're kind of tightly coupled. The third normal form is tightly coupled into the storage engine of the relational database because in 1980, the idea of running ad hoc queries on denormalized data was crazy talk, right? There was not enough throughput in the system. The storage subsystems couldn't handle it. The CPU couldn't handle it. So the only way to be able to run ad hoc queries was to normalize the data. Today, we don't really have that problem so much. And what we really want to do is we want to optimize the data structures for the most frequent access patterns, right? So what does that mean? That means, well, maybe we're going to create a rich embedded document structure where we push everything into it, an embedded relational structure. Maybe we're going to create multiple documents and we're going to mix and match. And some of those documents might have some embedded relational data and others might have some denormalized data and whatnot. But it all depends on, how is the application actually using the data, right? So again, it's like kind of one structure is very rigid. It's just the way we're going to relate data. We're going to store relational data. The other structures are more fluid, right? And they really depend on how the application actually uses the data. And we'll get into that. So what the reality is the optimal grouping of objects into documents or collections is determined by the workload, right? There's not a lowest common denominator. Like in the relational database, we have this third normal form, right? We're agnostic to every access pattern. We're optimized for none. In the case of the NoSQL database, what we found at Amazon was that the patterns that matter are the ones that run hundreds of times a second. Okay? The patterns that don't are the ones that run once a day, once a week, whatnot. So what I really want to do is I want to drive efficiency into the high-frequency access patterns, and the way I do that is by optimizing the data model. So what does that really mean, right? How does this really work? When we break all this down and we start talking about structuring data according to the way the application uses it. So to understand what is really happening and when we move data around, we kind of need to understand what happens and how document storage really works, right? So unlike row column store, where every single row is the same size, documents are all different sized, right? And when documents get written to disk, they go through a very complex process, but really the only thing we really care about is this thing at the bottom end. It's at the back end of the whole thing. It's the block manager. The block manager is what determines what gets written to disk and how, okay? So if I have large documents being written to disk, the block manager is going to package those up into consecutive blocks. It's going to write them out to disk. They're going to be very easy to read. Okay, if I have a bunch of small documents being written to disk, they're going to get packaged up together with other small documents if they're smaller than a single block, and they're going to get written to disk with other things that are not related to each other. Now, what does that really mean? It means that when I read the large document that's rich and embedded and stored across consecutive blocks, it's going to be a single consecutive read. When I read the small documents that are related to each other, I might be bringing things into memory that I don't really care about when I go access that data. So how the block manager is packaging the data is very important to us, but only because we need to understand how is the data actually being read out of the system. And what it comes down to is that in document store, like in MongoDB, we use Wired Tiger as a document storage engine. It's an append-only file system. What that means is documents don't really get updated where they are on disk. If I update the document, it's going to write it to a new location. It's going to update the index with the new pointer to that location. And documents, as I discussed, that are less than 4 kilobytes of compressed data are going to be aggregated into single block writes. So this means related data that's stored in multiple documents is going to fragment over time. So in essence, if it's a high write velocity workload, that's not going to hurt me too much. Because in OLTP workloads, we're often very, very write heavy. Right? What we found at Amazon is that almost 90% of our access patterns were writes. And it's because OLTP data gets written a lot, updated a lot, but it very seldom gets read, right? So it's not the read operation on most OLTP workloads that are going to hurt me. It's the write operation if it's not efficient. So writing small documents is good. So high velocity workloads, read workloads, benefit from those large embedded documents. As we said, they get written into consecutive blocks. When I read it, it's a nice clean read. I'm not thrashing my cache. But high velocity write workloads benefit from multiple documents as opposed to rich embedded documents. Why? Because think about how the access pattern is working. If I'm writing small bits of data that are related to each other and I'm compiling them into a very large embedded document, then as I add or update small bits and pieces within that document, right, I'm going to cause the system to move data that it doesn't need. All right? When you're moving data that you don't need, then you're causing inefficiency in the system. Essentially, if it's a high write velocity workload, write the data, write the data, write the data. Don't worry so much about the cost of the read. It's not happening very much. Now, hybrid workloads, right, where we have, I don't know, maybe a mixed amount, 50-50 read-write, we're going to start to play with things like covered indexes, right, in-memory working sets to make sure that the file system cache isn't getting thrashed as much as so much it's going to start to hurt performance. So there's always ways to accommodate the workload, but we need to understand this right away when we're working with data modeling in NoSQL. Is this a read-heavy workload? Is this a write-heavy workload? Is this a hybrid workload? What kind of data model am I really trying to build here to support, you know, this particular workload? So, and what it comes down to when we start to figure out what we're going to do is it really comes down to avoiding anti-patterns. And there's only 2 anti-patterns that we need to avoid. The first anti-pattern we kind of discussed a little bit is the over-embedding. Creating documents that are too large, they're larger than they need to be. Or more, it creates an inefficient access pattern that causes us to waste a lot of resources, right? So schema patterns, when you get into over-embedding, it's about, you know, these 3 areas, right? Data is either going to be unbounded. When data is unbounded, what that means is maybe I'm adding data to the document. I've got a one-to-many child relationship I'm trying to express, and I'm expressing that as an array of objects inside of a parent document. Now, as I add documents and I add subdocuments to that array, the parent object is going to get bigger and bigger and bigger. If this is an unbounded process, then that's eventually going to drive a lot of inefficiency in the system because I'm adding small bits of data to the document over time. Document gets bigger and bigger. The cost of every update starts to get larger and larger. So unbounded data, things we want to avoid, right? Arrays that grow and grow and grow and never get trimmed. These are things we want to avoid creating in our embedded document structures. The other thing that happens is data can be unrequired, right? I might be retrieving data that's not always needed or not always required when I go get the data, right? So things like, you know, if I have a document for a customer and every order for the customer is stored in that document, then when I go update one order, I've got to get all the data for the other orders as well. So that's absolutely data that's not required all the time. Maybe I only need all the data when I go select all the orders for a given customer, but I don't need all the orders every time I update any order, right? So this is an access pattern where maybe I'm pulling data back that's unrequired. And then the third thing that happens when I see this all the time, I see it in every database, is that data is just unneeded. Okay, oftentimes as developers, we're going to store data in the system and you ask the developer, why is that there? And they say, well, because I thought I might need it. Well, if you thought you might need it, then you don't really need it. So maybe it doesn't need to be stored in the database until I actually need it, or it should be stored somewhere else in a blob in a document in S3 or something like that. But the reality is these are the areas that we're going to look at when we're looking for over-embedded documents, right? Things where we have unbounded arrays. That's the most common way that we see, you know, over-embedding. Unrequired data is the next most common way, and then, of course, the unneeded data. Let's avoid those 3 things. So that's if we kind of take a look at that, at our documents through those lenses, then typically we can get rid of 90% of the over-embedding problems that we have. The other problem that we run into is, and it says normalization, but that's not necessarily an anti-pattern, but over-normalization certainly is an anti-pattern in NoSQL databases. and you know, what does that mean? You know, what it really means is when we store data in the database, we want to store it the way we actually use it. Relational databases actually seldom do that. A relational database is an abstraction of the data from the application, and is, in the example here, we're talking about a product catalog. It becomes pretty obvious, right? We're not going to store product information in a relational database like this, because deconstructing it and reconstructing it every time I need to go get a product by ID or a list of products by category and type or sort by whatever, it's going to be a lot of work that the system's going to do. So as developers, we kind of already know we're not going to do that. We're going to store those documents, those objects as documents, maybe even a cache in front of that relational database. But the reality is it's probably better to just use a database that stores the data the way the application uses it. Right? Embed those rows right into the document structures I'm getting, because I'm getting products by ID, products by type, products sorted by price. Right? I want the data that's already joined. I don't want to have to go join it together to produce it. Right? And as developers, we kind of already know this, so we're going to store this data as objects. And that's the best part about NoSQL. Right? NoSQL gives us the ability to store data objects in the database exactly the way the application actually uses them. So it's a much more efficient process to remove the abstraction of the data from the application. And it's something that developers actually start to find to be much more natural. Once we work with the teams that our customers and the teams that our customers have to understand how to model their data efficiently for their workloads, the most common comment I get is that's kind of how I actually built my application layer objects. And we get to store those in a very similar shape, right? So that's actually very natural. Now, when we talk about NoSQL and data modeling for NoSQL, there's a whole bunch of patterns that we get into, right? Certain data modeling patterns, and every one of these things has a place and a time to be used, but not everyone gets used all the time. The trick to NoSQL data modeling and doing it efficiently is being able to identify when these patterns apply to your particular workload. It's actually what my team does. Right? We spend a lot of time working with customers to understand exactly what their workloads are, how they actually access their data, to come back and show them which one of these patterns make the most sense for your workloads. And that's the same process that I ran for Amazon. I ran for AWS. I now run for MongoDB. It's really an enablement exercise. One of the things that I love doing and working with our teams is what we call design reviews. Right, where we sit there and we spend an hour with the team, we catalog their use case, we catalog their access patterns, we understand exactly how they're working with their data so that we can advise them how to build those document structures. And what it comes down to is when do I break things up? Right? When do I use one document? When do I use multiple collections? When do I use a single collection with multiple types of documents? Right? And those are the questions that we need to answer. Do we use, on the left, we can create one rich embedded document. If we go back to our use case, which is the forum, articles, that people write articles, they comment on articles, whatnot. Articles have tags and comments. I can choose two ways to go here. I can say, okay, let's create a rich embedded document for the article. I'm going to denormalize all the personal information for the people who are contributing to the article. We're going to embed the comments. We're going to embed the categories and tags for the article. That's certainly a valid way to go. But if you think about this, articles, again, some articles are going to get lots of comments. Some articles aren't going to get so many comments. So the articles that have few comments, this is probably a fine data structures. For articles that get lots of comments, not so much, because those articles are going to grow and grow and grow as the comments come in. So maybe the structure on the right is going to be a little bit better, where we try to maintain some sort of relationship between these documents. And how do we do that efficiently in a NoSQL database, right? I thought, in a NoSQL database, we don't want to create multiple collections and relations between collections, and that's true, but that doesn't mean that we can't express the relationships between the documents, okay? And we can still do this quite efficiently in a NoSQL database using what we call the single collection pattern. When I was at AWS and DynamoDB, we called it single table. But the idea here is that in a NoSQL database, data that is accessed together should be stored together. Either in a single item or a single document, or as a collection of items or documents that are stored on a common table and indexed together on a shared dimension. And the reason why is because the relational database, essentially what its job is to do is to join those documents across tables that are indexed on a common attribute. Well, if I put all the documents in a single collection, I index a common attribute, then I don't need to join them. They're already there. They're already on the same index. So in this case, what we're going to have is we're going to have a couple of documents, and we're going to actually mix an embedded structure in here as well. So we're going to have an article document. The article is going to have all the data related to the article. It's going to have this array of pointers to the other documents in the collection that it's related to. In this case, it's related to itself. It's related to the person that wrote it. All right. It's going to have a couple of embedded objects in here, the tag information, the category information for the article, because I don't want to have to go find that or join that in when I go get the article. It's immutable data. Tags and categories are things that don't change. So let's go ahead and embed that immutable data. This is actually not a technique that's, this is a technique that's used quite frequently even in the relational world, right? If the data is immutable, it's easier to embed it onto a row than it is to go join it from a lookup table or whatnot. The same thing with people, right? People have an array of the articles that they've, the IDs of the articles that they've contributed to. Of course, they're related to themselves. Comments then are also related to the people that wrote the comment in the article that they are associated with. And now, if I index the related to attribute, right, in a multi-key index like MongoDB supports, I'll get an entry on that index for every entry that's in those arrays. And I can query and say, give me everything that's related to article ID A1. I'm going to get all the comments. I'm going to get all the people. Right? And I'm going to get everything that I need to be able to understand, who wrote that article, what comments were made on the article, and whatnot. And this is a great way to be able to reflect this relationship of things that are related to each other. But there's a couple problems here, right? And the first problem is that sometimes when I go to read the articles, I want to know, which are the most popular articles. And one way to know what the most popular articles are is which are the ones that have the most comments. So I might want to get a sorted list of articles by the number of comments that they have. And I don't want to have to calculate the number of comments every time I go get that list. So what we're going to do is use the computed pattern, right? That's one of those patterns in the list. The computed pattern is a way of kind of being able to create summary aggregations, summary counters. And as comments come in on articles, every time a comment gets posted, I can bump the counter on the article so I know how many comments articles have. Now I can easily sort the articles by comment. I don't have to actually compute the number of comments every single time I want to get a sorted list of articles by number of comments, right? So this is what we call the computed pattern. Again, I use this in relational databases as well. Quite frequently, it's a technique that's used because we don't want to, the cost of counting rows is not cheap in large workloads, right? So it's a nice way to be able to say, okay, I'm going to sort my articles by the number of comments that they're receiving. The next thing that might happen is if we talked about storage, right? How the block manager works. Comments don't all get written at the same time. They get written over time. People reply to comments. That list is going to grow and grow and grow. And we always are more interested in the more recent comments, right? When I go look at an article, I don't really start with the comments that are 3 weeks old. We start with the more recent comments, right? So the reality is, as we talked about the way that block manager works, I'm going to start thrashing that file cache pretty heavily as I start to read the articles and the comments this way, right? If I go get an article and I say, give me everything that's on the related to, it's going to go out and it's going to get a bunch of documents that are located all over the disk, right? And it's going to bring in that data into memory, and that data is going to come along with other documents that that was written along with that it's not related to, so it's essentially causing some file system, some cache thrash, right? Which may or may not be a problem, depending on the size of the instance, the amount of data. If it all fits in memory, not a problem. But if it's a large deployment and we got a lot of heavy usage, we can start to see some performance impact because we're just evicting data from memory too quickly, and we're bringing data into memory that we don't care about because of this. So the next thing I might do is I might say, okay, look, when I look at the article, I always want the last 10 comments because I want to see the first page of comments, and let's go ahead and embed those comments into the article so that I only need to go back and get those individual comment files when I need to go past the first page. Maybe 99% of my users, they never go to the next page. They only read the first page of comments, maybe the first couple of comments. They just need to see the latest what's been said, right? We're not going to go paging through. Some users, of course, will page through, and that's okay. That's a subset of the use case. If you look at your access patterns, get next page is going to be a very low frequency pattern, whereas get me the article and the first page of comments is going to be a high frequency pattern, right? So every time a comment gets added to the article, we're going to create the little comment document. We're going to write that in there. We're also going to embed the comment into the comment array on the article, and we're going to evict anything that's more than 10 comments old, right? So always the last 10 comments live on the article itself. When I go select my documents, now I've got a nice efficient way to get my documents out of the database. I can sort articles by number of comments. I can get the top N articles. I can display those in the users, as they paginate through the articles. I can display each article document, and I can have the last 10 comments for each one right there handy. So all the information that I need is in my hand when I go read the article. but I have secondary access patterns. Get me all the articles for a person, right? Get me all the people associated to an article. Get me all the comments associated to an article, right? Things that run at low frequency, the things I really don't care about the efficiency because they're not running hundreds of times a second. Get article by ID is my most common access pattern. So I'll optimize for that. So giving me the computed pattern and the subset pattern, embedding that data into the article document gives me real fast access to the articles on my primary access pattern. The data is immutable. I don't have to worry about the data that's updating inside the document. So this is a very nice way to talk about how we can use both the single collection pattern to satisfy our secondary access patterns, but our primary access pattern is really leveraging the embedded document structure because it's much easier for me to read that document, right, and get the data I need whenever I need to get it. So the idea here is, again, correct does not always look the same because depending on how I'm actually reading the data and what data is relevant to me, I may or may not want to embed those comments, right? How are we reading the comments and whatnot? So the idea, again, is understand, how is the actual system accessing the data so that I can actually build a document structure and a data model that works good for my service, for my application, and for my workload. So signs of trouble when you get into schema anti-patterns. How do I know that I'm probably doing something wrong? Well, the first thing that I see teams doing wrong is optimizing the wrong pattern. All right, this is the most common problem that teams have. And to kind of illustrate this, we'll talk about an order processing workflow. The orders get created. Orders have items, they get processed, they get shipped, whatnot. They get updated at fairly low frequency, but they get read quite frequently. And so if we look at our access patterns, and this is the process that I go through with every team, every design review I have. What's the nature of your data? What are the entities? How are they related? How are they accessed? What are your access patterns? And we're going to build this little matrix here that talks about what your access patterns are, and what's the frequency of those patterns so we can understand what the most high frequency patterns are. Those are the ones that matter. Again, if it's running hundreds of times a second, I want that thing to run as efficiently as possible. If it runs once a day, once a week, whatever, I just need to make sure it responds in a reasonable time frame. I don't care about the efficiency of the query if it's not running at high velocity. So in this particular case, we've got an order processing pattern. We've got 3 access patterns that we're going to try and support here. The first one is create order. They hit that about 1 million times a day, 500 requests per second at peak. So we definitely want that pattern to be highly efficient. The next one is get view order, right? People come and look up the order. It happens at much lower rate, obviously. Again, OLTP applications are very write heavy. People will oftentimes cause actions that create data, write data, update data, but they never look at it unless there's a problem, right? So the read patterns are typically lower than the write patterns in most OLTP workloads. So here we're reflecting that. The create order pattern is much, much higher than view order. And then at the end of the day, we've got a get product summary workflow, right? Get me all the products that were sold today, the quantities and the revenue for each product and whatnot, and generate a report for the business that runs nightly. Now, a lot of developers are automatically going to say, well, that's a report I got to run. I got to optimize that pattern. And what they're going to do is they're going to create an index to support that workflow that's going to look something like this, right? It's going to be on the SKU, on the order date, and we're going to go ahead and then read that data at the end of the day. But the reality is that during the day, I have to maintain that index. My heaviest workflow is my create order workflow, and it's peaking at 500 requests per second, and every document that hits the system now has to update this index for every single item on that order. Now, I mean, it's not a lot of overhead, right? A lot of the things I'm talking to you right now, they're not a ton of overhead, but when you start running these things at 500 transactions per second, 1,000 transactions per second, or prime day type of workloads, this can make a big difference, right? This can actually be a lot of cost here. So maybe, and the reality is, I mean, how much are you actually benefiting from this? Maybe the reality is we don't want that index, and it's okay, we'll do a collection scan at the end of the day. Heck, it's only 1 million orders. Yeah, it'll take a couple of minutes for that report to run, and it's going to be less efficient at the end of the day, but so what? It's happening at midnight, the system's offline, nobody cares, you're not processing orders. Let that system do a little extra work at the end of the day instead of doing all that extra work during the day so that query runs efficiently at night. It doesn't make any sense. Again, optimize the patterns that matter. Right? The one that matters is the right pattern. Make sure your right path is as clean as possible. Don't over-index. Don't index for access patterns that you don't actually need, whatnot. The next thing that happens is we get containers with more data, right, than we need. We talked a little bit about this already, but if we were to say, let's take this order processing workflow and turn it into a shopping cart instead of a finished order, right? So in a shopping cart, there's an interesting access pattern I found when I was working with the Amazon team. It's the add remove item pattern, right? I'm very guilty of this. I'm sure we all are. When we use a shopping cart, we kind of use it like its own little database, right? We add items, next day, tomorrow, I go in there, I go, oh, I need to get something, and you look at your order and you go, oh, I don't want this, I don't want that, I don't want this, right? So if you think what's happening on the back end there, and in a relational database, what's happening is you're adding rows and deleting rows from a table, right? One of the things we found at Amazon, which was quite interesting, was that 70% of the access patterns actually hit a single row of data on a single table. Okay, 20% hit a range of rows on a single table. So what it's telling you is your applications are using the data in bits and pieces. This is across 10,000 services deployed across 3,000 Oracle Server instances, right? So pretty good data sample here, and it's very consistent with what I've seen with other enterprise customers, right? Applications use data in bits and pieces, but it's the join patterns that cost us, right? The last 10% of those access patterns were responsible for driving 50% of the infrastructure utilization, right? So if we can optimize those joins and remove those joins, we're going to remove a lot of cost from the infrastructure here. Now, in this particular case, by adding items and removing items from the shopping cart document, I'm creating a document that's essentially moving data I don't need whenever I add or remove an item. Right? I don't need the whole order when I go add an item. I don't need the whole order when I go remove the item. But if I'm storing them as embedded documents in this document, in this shopping cart document, that's exactly what's happening. Now, depending on the nature of the system, that can actually be a lot more data than I'm showing you here that's being added and removed, right? In Amazon, all kinds of notations about fulfillment center locations, shipping dates, delivery dates. There's about a kilobyte of data that got added to a shopping cart when you added an item to the shopping cart. So that's quite a bit of data that's moving around. If I have large carts, that's a lot of extra data that we're moving around that we don't need, okay? So here we go to look at, and again, we're looking at a very write-heavy workload, right? Shopping carts oftentimes get created, but they don't get processed very often. They only get processed when I hit the button and say buy. But I'm going to add items and remove items from that shopping cart many, many times. Most people will execute the add remove operation multiple times before they actually buy the cart. So the way to actually make that work a little bit more efficiently is to do two things. First thing we're going to do is we're going to remove the items from the embedded document structure, and we're going to create a document for each item. This is more or less the way that the relational database would look at the data. Right, I would have a shopping cart table, I would have a shopping cart items table, and as I add and remove items from the shopping cart, I'm just popping and pushing rows onto that shopping cart items table, right? Nice and efficient. So I've created the same kind of data structure here. I can actually add items to the shopping cart by just prefixing the item ID with the shopping cart ID. So the underbar ID of the document that describes the shopping cart, the actual metadata for the shopping cart, that's the shopping cart ID. And then underbar ID on each document that describes an item on the cart is prefixed with the shopping cart ID and then appended with the SKU, right? So I can have multiple types of items. I can interact with these items independently of each other. I can add, remove items to the cart. And the cost of each individual update is just going to be the size of the document that I'm moving, right? The item that I'm adding. Now, granted, it's going to get written along with many, many other items and smaller documents it's not related to. But again, this is a very write-heavy workflow, so I really want to optimize the write path. And that was apparent in the data look, right? If we look at the add remove item, immediately is 20 million add remove items daily and 2.5 thousand add remove item operations per second at peak. Obviously, that's now the operation that I want to optimize the most, right? So again, key thing here is to understand when to embed, right? When to use separate documents, when to use single collection, when to use referencing, when to use all these other patterns that we have. There's dozens of them. But there's always a way to be able to apply those patterns to actually optimize the workload and avoid the inefficiencies. So the last thing that I see that when I know we're going to have trouble is when people tell me that they don't use schema validation. Or that they don't do it well. They don't necessarily tell me they don't do it well. They'll say, yeah, we use schema validation, then we look at the validators and we go, oh, okay, all kinds of problems in this thing. And the reality of schema validation, we talk about document databases like DynamoDB as schema lists. But they're not schemaless, all right? Everything, all data has schema. When I put a document in there, I've got attributes, and attributes have values, and that defines schema. And oftentimes, and most of the time, I'm inserting many, many documents that look kind of the same. So there's a schema there. And enterprise needs to have some governance on the data that they're storing in these systems. One of the biggest problems I had with MongoDB or with DynamoDB was the fact that there was no schema validation. And I had customers who were actually using streams and Lambda interactions to do the validation of the data on the items that are hitting the table after they're inserted. With MongoDB, we give you first-class schema validation. You can validate everything, right? And you always should. You should always validate everything. Ensure that the required data is structured correctly, right? You can create logic. You can use JSON logic to determine what types of objects are acceptable in a given collection, what areas of the document have rigid schema. I always say avoid unstructured documents, right? Don't let users just put wild, wild west into the database because you don't know what they're doing. And if you have no limits on the type of schema objects that they can drop in there as extended attributes or whatnot, then you don't know what impact that is going to have on your operational workload. So try to avoid unstructured documents, right? Always try to validate everything that's going in the database. You can use JSON schema to actually validate business logic, right? You can use query operators on field values within the document to verify ranges and value sets and conditions in the data. And also, don't just write a validator and confirm that things can be inserted. Confirm that the bad data fails, right? So oftentimes it's funny how people will write a schema validator and they won't verify that the thing will fail if they add attributes that they shouldn't have, or if they put values in those attributes that they don't want. So always make sure that your unit tests are trying to insert good data and bad data and failing on the appropriate conditions as well. So schema validation is a very, very important part of any database, and again, first-class citizen in MongoDB. So what we're coming down to with all of this is that it's about aligning your schema with how the data is used. Right? What are your access patterns? What is your workload? What is the nature of that workload? Oftentimes when I start my engagements with customers, those are the first questions I ask, the first thing I say. Treat me like a developer that's joining your team and you're telling me what we're doing. Right? We're describing the data, we're describing the workload, you're telling me about your access patterns. We want to understand what are the things that are most important. Right? Those queries that run hundreds of times, thousands of times a second, we're going to prioritize those. The other ones I need to know about because we got to be able to accommodate those, but the ones that are most important are obviously the ones that run a lot. So we're going to get into a couple of real-life examples here. We're going to actually break down some workloads. So the first thing we'll talk about is a benchmark that's pretty widely recognized in the industry for order processing, uses a similar schema to what we just talked about, but it's TPCC. So a lot of people think that denormalization means increasing the size of the data on disk. What's interesting is actually when we went through the exercise of reproducing TPCC with MongoDB is what we found that the size of the data in index is actually decreased. And we thought about this for a second, but well, that doesn't make any sense because we are doing some denormalization in here. We're duplicating some data in these data structures and whatnot. But when it came down to it, if you think about how the row column store works, right? The row column store in a relational database, it expects every row to be the same size. Most of the rows aren't that big, but it's going to reserve that much size anyways, right? So when I store a row in a relational database, there's always a little bit amount of data that's getting burnt on every single row, unless the data is too big. If the data is too big, it's going to split the row and it's going to store the oversized attributes in off-row storage, and it becomes very inefficient to retrieve the data. So relational databases are great when the data bits are small. Relational databases start to stink when the data bits get big. Document databases, on the other hand, they only store the data I put in the document, no more. Right? Wired Tiger doesn't claim unused bytes or pack unused bytes into a write. It just takes the data that's given and shoves it onto the disk. So it's actually, the translation is that in workloads like this, OLTP workloads that have fixed size documents, we're actually going to save some data by denormalizing because the amount of padding that occurs in the relational database that does not occur in a document store. So that was the first interesting thing that we noticed, was that the size of the data got smaller. The other thing we noticed was that the size of the indexes got a lot smaller. And why is that? Well, that's because in a relational database, I'm indexing the same value across many tables, and the number of children is going to affect the index size. Because the parents are going to have one parent to many children, so the indexes on the child tables are going to be larger than the indexes on the parent tables. Whereas in a document store, those embedded relationships prevent the index from growing because there is no child table. Essentially, the child relationships are expressed within the parent documents in this particular workload, so we got away with smaller indexes and smaller data footprint, which was kind of interesting. But the next thing that happens is because we're moving less data around, we're not joining data to produce order views. We're doing simple key value lookups on order ID. The other thing that happened is we started to see throughput improve as we increased the number of threads. You can see very consistently 15 to 25% more throughput with a document model. That is directly related to the fact that we're not joining data to produce. Not every access pattern in TPCC requires joining of the data. Most of the access patterns are add and remove rows from tables, right? Add a shipment, add an item, whatnot. But the ones that say get me the order, that's the expensive part, right? This is what drives utilization in the relational database. When I go to join things, they're very high time complexity operations. So we saw increased throughput, right, from the embedded model. Okay, so embedding is not always going to increase the size of the data on disk. Embedding is not always, is definitely going to increase the performance of your system when you're joining data, right? Because I don't have to go and get data across multiple containers. Now, one thing that happens if I don't embed correctly, bad things happen. Now, in the model we just showed you, it's embedded correctly, right? All the items on the order are embedded within the order document. But if I were to create a little different data structure, I'd say, you know, I'm going to create an order per customer or a document per customer, and I'm going to embed the orders in the customer document, then you can quickly see how it's just going to fall off a cliff as the order document gets bigger and bigger and bigger and bigger, or the customer document gets bigger and bigger as we add orders, right? The performance of the system falls off the cliff eventually as the data gets too big, right? So good embedding versus bad embedding is going to leave totally different results, give you totally different results. All right, so one of the last examples I'm going to talk to is one that I've actually worked with many companies in many ways, right? So this is a real-time trading example. It's also the same thing you see in payment processing systems, right? Anywhere where you have some sort of a transaction or an authorization or an order, and then you have executions underneath it, right? So in this case, the team I was talking to was a large bank in Europe. I was talking to with MongoDB. I ran into this use case at DynamoDB on the AWS team as well. Again, most financial institutions have some sort of application that works this way. In this case, it's about trades and executions. So trades happen. A trade is an order. Executions happen. These things are events that are coming from a downstream system. They don't need to authorize the execution against the trade. It's really just an event tracking system. And at the end of the day, what they want to know is, are there any trades that haven't been fully executed? So during the day, they're just simply aggregating. Here's a trade order, here's an execution, here's a trade, here's another execution. Most trades only have one execution. Some trades might have many executions. But if you break down the workload, this is what we saw from the company that we were talking to, and very consistent with the other trading houses or financial service customers we talked to, is that the insert trade operation, it happens, they get about 25 million trades a day from this particular service provider, and they're peaking at about 25,000 requests per second because 90% of their trades come in the first 5 minutes of the market open, right? It's like, boom, everything floods in. After that, it's pretty steady state, pretty trickles in, unless there's like some big market event. But for the most part, the first 5-10 minutes of the trading day, that's when all their business lands, okay? Executions come in up to 75 million a day, again, peaking at 75,000 requests per second. And the customer I was talking to was telling me, and then they had a third access pattern, which is get trade, which is very infrequent. This is like customers calling, why is my trade not executed? Let me go get the trades and executions from the system and see what's happening here, right? Kind of forensic analysis, whatnot. And that's below 1,000 per day. But the big problem with this workload was that they were telling us it's too slow, right? MongoDB is too slow for this workload. We can't do this. And what it came down to is that it's because for a couple things. The first thing was that they created an index on the trade ID, right, to be able to go support the trade pattern. And that's creating overhead on every trade that gets written because they had an underbar ID which contained an object ID, which we generated for them because they didn't give us one. Trade ID is guaranteed unique, but they didn't use it for underbar ID. So what ends up happening is you create an underbar ID index, that's the default index on a MongoDB collection, that's a write-only index. There's no read pattern on it. So if there's no read pattern on that index, then essentially it's a wasted chunk of resources that I'm maintaining every single time I insert a document, right? On top of that, they create another index, a secondary index on trade ID that has to be updated every time a document is written with the unique value that describes the trade. So The update operation is actually slower than an insert because I got to go get the document, I got to add the data into it, I got to write the document back into the system, right, in an append-only file system. So there's a bunch of things happening here. I got a write-only index, I got a secondary index I don't need to maintain, I got an update operation instead of an insert operation. If you think about how trades and execution work in a relational database, right? It's a trade table, it's an executions table, it's rows on tables. It's exactly the same thing we got going on here, so I need to be able to represent this data as rows on tables, right? And that's exactly what we did. So we told them, look, let's get rid of that secondary index, okay? Let's create that data structure similar to what we saw before, where we're gonna have the trade ID as the underbar ID. Every execution is gonna come in, you're gonna be prefixing the trade ID on the execution ID, and you're gonna append the execution ID to that. And now, if I wanna get a given trade, I just, the query becomes find where underbar ID starts with trade ID, right, with an anchor regex condition. This gives me the ability to go get the trade when I need to, granted maybe not as efficiently as it could be because I'm getting data from different documents that are written at different times, but that's okay because it's an uncommon access pattern. But it took all the overhead off of the writes. This improved the performance 2 to 3x. So it essentially made the system usable for the customer when they had a system that was unusable, before. Okay, so in the end, what we end up with here is the causes of poor database performance, and I know this says 1, 1, 1. It should actually say 1, 2, 3. But the reality is operation is inherently slow. Okay, maybe we're just doing something that should take a long time. I'm doing a collection scan on a terabyte collection. I know I'm doing this because it happens once a month or once a quarter or whatever, and I'm not going to optimize it, and I'm okay with that. It's just slow. The other one, the next one is it's inefficient schema or query design. We blew it. We designed something that maybe wasn't exactly as efficient as it could be. We didn't choose data structures that, well, and we're doing work that we don't need to be doing. And then the last one is it's inadequate or poorly tuned hardware, okay? But of the three things that I work with, the one that happens the most is it's just inefficient schema. Most of the time when I hear people tell me I can't use NoSQL for my workload, I can't use the database for, for what I'm doing, it's really because they're just not using it correctly. And that's one of the reasons why my team focuses so much on enablement with our customers, right? I mean, our function is not about sales. Our function is about showing people how to use the technology most efficiently, having these kinds of discussions where we break down your workloads, we talk about your access patterns, and we just give you a breadcrumb trail. We found oftentimes developers are pretty smart about figuring things out once somebody shows them where to get started. Where you fall down is sometimes just figuring out where to get started, right? So being able to clear that brush, that's really what my team's focus is helping teams get over the hump with data modeling like this. So thank you very much. I really appreciate your time. Hopefully this was a good session for you.